Thanks a lot for having me. Yes, so we heard a little bit about the ethical and governance aspects of open models, and we also not just heard about legal. I'm going to talk a little bit more about technical and organizational aspects of training open language models. And before I dive into the concrete projects that we worked on and I want to highlight, I just want to take one step back and show a little bit like that we kind of now are in like a second spring of open models. If you look back at the origins of transform models in the very early days, all models were kind of open. Google released BERT, OpenAI released GPT, and later GPT-2 after some waiting. But then came kind of an open winter, so OpenAI stopped releasing their models. Same for Google. Meta was still trying to releasing some models, but got like a lot of backlash when they did. And so if you look back roughly a year ago, if maybe in January, December of 2022, 2023, it wasn't so clear if there wouldn't be many open models in the future. And luckily, that has turned a little bit. So on the one hand, Meta released Llama 1 and Llama 2 last year. Recently, they announced that they are investing in a huge GPU cluster to continue training these open models. Even more recently, DeepMind released Gemma, which is a small Gemini kind of model that they released openly. And we also have startups like Mistral that are continuing to push open models. So things look a little bit more hopeful now. Also, if you're not a big industry lab, there's hope that you can train open models. If you just look around in Europe, there is a lot of open compute clusters now that are open to researchers. For example, there's Lumi in Finland with 10,000 GPUs. There's Jewels and Jupyter in Germany that have combined like 28,000 GPUs. In Italy, there's Leonardo with 13,000 GPUs. And currently completing in Switzerland, there is Alps, which will also have like 10,000 GPUs, and I think the Swiss AI Alliance will use partly. So there are compute resources to train these open models. You don't necessarily need to be at a big academic lab, not academic industry lab, to build those models. So I think that's another good step. But when we talk a little about closed and open models, I want to just highlight a little bit that there's differences in how open or how closed it is, and some of the aspects go into the talks that we just saw. So on the one extreme, we have the closed models that are just accessible via an API. Models like GPT-4, Gemini, or Claude are such models. You can't run them locally, you can't download them. Researchers don't have any access to their internals, so we don't really know what's going on in them. And as a user, you're very limited in fine-tuning these models. For many use cases, you get a big performance boost if you fine-tune such models on your concrete data. But you can only do what these APIs offer you. Some offer fine-tuning, some others don't. Some models get outphased. You're kind of at the mercy of whatever the API what they decide to do with the API. Then kind of in the middle, you have what I would call like open model weights. I wouldn't say those are fully open models. The only thing that's actually released is the modeling code and the weights, so you can run those models. That's already a great step forward compared to the closed models, because you can now host them locally. You don't have to send your data for inference to another server. And you can fine-tune them however you see fit. But they still have some limitations. So as a data provider or content creator, you don't know if your data was used in the data sets and you don't have any way to remove your data if you don't want your data to be part of such an effort. You can't inspect the models for biases. This is not only like biases like the traditional biases, but also like many of these models are aligned, and you don't know where on the political spectrum this alignment happened. Clearly there is somewhere on the spectrum, but you don't really know how, for example, the data was annotated that went into aligning. From a scientific perspective, we can't really be sure if some benchmarks that we're evaluating those models on weren't somehow in the pre-training data set. And we can't easily reproduce those models if we don't have access to the data. So that brings me to the third category, which is the fully open models. And a fully open model requires that the model is released, the pre-training code is released, and the data set is released. We heard about Bloom and Big Science as one example. There is also Olmo from LLMs, which is a fully open language model that was released a few months ago. And one project I was part of, Big Code, built a star coder where also all the model code and data are released. Also, this has some drawbacks. So if you're a startup that's aiming at building like high-quality LLMs, if you release everything, you might give away your competitive edge. Also, if you're fully transparent about what data you used, makes it easier to potentially sue you in the future. And if you ever build like any open source library, if you open source something, it comes with the burden on maintenance. So you need to make sure everything stays up to date, the code is running, and so on. So it's a little bit more work to do this. So I want to talk about these two projects. Jada already talked a little bit about Big Science. I'm going to talk a little bit more about like the motivation and the organization and how we built the data set. And then I want to talk about Big Code, which is kind of the successor of Big Science. So the inspiration for Big Science was that when the project started was around a few months after GPT-3 was released, and we started to get into this phase where it wasn't so clear anymore if somebody else would build an open GPT-3 model. So the idea was, can we do something in the open and kind of draw inspiration from, for example, the Large Hadron Collider in Geneva, where we say, we find the compute and we bring researchers together and we build things in the open in a transparent way. And it turned out that a lot of people were very interested in doing that. So I think there are over 1,000 collaborators from dozens of countries and many working groups that were interested in investigating many different aspects of training such a large language model. The first step, usually when you want to train a large language model, is you need to build a large high-quality data set. And one aspect that was important to Big Science was, in contrast to GPT-3, this data set should be multilingual. We don't just want to focus on English, we want to make sure we have some representation across like a wide range of languages. And to create a large data set across many languages is challenging. And the main building block to address the challenges was trying to get native speakers being involved in the data preparation. So the roots corpus, which is the data set that we use to train Bloom, has kind of three pillars. The first pillar is sourcing high-quality data. That's data sets that these native speakers said those contain high quality. For an example could, for example, just be Wikipedia in the corresponding language. Then the second pillar is identifying kind of high-quality domains. So rather than just taking a web corpus, try to find like domains within the web that contain high-quality data. Could, for example, be a news outlet in a certain language or some, I don't know, documentation. And then the third pillar is taking, it's hard to get to the volume that you need to train these large language models. So with the first two, you get like a high-quality data set, but it's still not large enough. So you still need to mix in a little bit of web data. But to make sure it's as high quality as possible, those native speakers, again, looked at the data and tried to come up with filters to remove as much garbage as there is in these data sets. So that's the roots corpus that we built to train Bloom. It's roughly 350 billion tokens, 1.5 terabytes. At the time, it was a very big data set. If one now, like 1 to 2 years later, 300 billion tokens seems like not so big data anymore. But nevertheless, we trained Bloom, 176 billion parameter model on Jean, which is a French public supercomputer. And it took roughly 3 months on 400 GPUs to train the model on these 300 billion tokens. So now I want to switch over to Big Code. Big Code is kind of the spiritual successor of Big Science. The motivation was very similar. At the time when we started thinking about Big Code was the time when Microsoft and OpenAI released Copilot. And so we thought it would be great if there would be like an open alternative to like the powerful Copilot models. And Big Code is organized similarly as Big Science in like an open way. Any researcher can join. But it's led by Hugging Face and ServiceNow. So Hugging Face and ServiceNow are sponsoring the compute to train the models, and they also take like a leading role in deciding what models to train and organizational aspects. But the spirit is pretty much the same. We want to have full data transparency. We want to release all the code necessary to process the data, to train the models, and we want to release the models openly with a commercially friendly license, at least. It's not a fully open license, as we heard before. It's also a Rail license, but we try to modify the Rail aspects such that it's much easier for companies to train models and deploy those models. How do you build a big data set for code models? So what we did is this few-step process. First, we went to GitHub Archive, which is an archival solution that kind of scrapes everything that's happening on GitHub. And we used the archive to get the repositories that exist on GitHub. That's roughly 220 million GitHub repositories. What we then did for, I think, roughly 3 months is just git clone. So we cloned all these repositories, took quite a lot of time, and then we had them all locally. Roughly 137 repositories were still like reachable, 50 billion files and 100 terabytes of data. On top of that, we added a little bit of file filtering. So we don't want to train, for example, on binary files or files that are very large, things like that. So we had a filter to remove files that we know for sure we don't want to train on, that already removed roughly 30% of the data. And then we applied license filtering. So we only used files that have permissive licenses, code files that have permissive licenses. And that gave us roughly 6 terabytes of raw source code. We applied a little bit of near-deduplication on top, which we found makes the performance of models much better if you do that. And that gave us roughly 3 terabytes of data at the end. So that's already twice as big as the data set that we built for Bloom, and that's just for source code. Recently, just like 3 weeks ago or so, we released the Stack v2. What I just showed is Stack v1, where we teamed with Software Heritage. That's also an archive for source code. And with their database, we increased again the size of the data set. So the data set size I showed before, after filtering, was 6.4 terabytes. Now it's over 60 terabytes. After the duplication, we still have 30 terabytes left. We increased the number of languages that we train on from 80 to 600. And just the training data set for the first iteration was roughly 200 billion tokens. Now we have almost 1 trillion tokens of source code. So one thing I want to highlight that we do a little bit different than many other projects that train models is we have a data inspection tool, so anybody can check whether their data was used in our data set and for training. It's an app called Am I in the Stack? So you can enter your GitHub username, and it will show you which repositories were part of which versions of our data set. And if you would like to not contribute to that effort and you think your data shouldn't be used for that, there's an opt-out mechanism. So you can kind of click there on a link, and it will open an issue on our GitHub page, such that we can verify that you're actually opting out your own project. And that way we can remove your data from future iterations. And you can see, I think it's a little bit blurry, but at the very top, we now have almost 2,000 opt-out requests that we apply kind of on a rolling basis. So I want to finish just with a few challenges when you build models in the open, fully transparently. One is that decision-making can be a challenge. So big science was a very democratic, very flat hierarchy. In big code, we decided to be a little bit less flat. So ServiceNow and Hugging Face are kind of a leading role in trying to make decisions, but still trying to take in as much feedback from the community and work with the people as possible. But decentralization can make decision-making more difficult. You have much more public scrutiny. I think it took roughly 12 hours after we released the Stack version 2 until someone sent us an email and said, like, I found my GPL code in your data set. It shouldn't be there. So if you release your data set openly, everybody can go and check what you did and find your mistakes. For that particular case, it turned out... Oh, I'm back. It turned out that somebody committed a Python environment into their Git repositories, which doesn't include the license file. So there's no way we could have seen it. As I said, maintenance is a thing, so we need to update our data sets. We need to apply new opt-out requests, for example. The last thing, that's maybe not obvious, but it's like if you're fully transparent also in terms of timelines, there is like other teams that build similar things that try to maybe arrange their releases according to yours. And we had in the past a few times for like some models were just released a few days before our model, which can be a little bit stressful. Yeah, with that, I would like to conclude my talk, and maybe we have a minute or so for a question.
Yes, one question. Thank you very much, Leandro.